Okay, boys and girls, today we're doing a little bit of area work, and we just basically have to lay down the groundwork so that we can understand area. The natural place to start would be with a rectangle, such as this one. A rectangle with just, a lot of times we call them quadrilaterals because they have four sides. The peculiar feature for the rectangles are these right angles everywhere, 90 degrees. So what we mean when we say area is we mean that these shapes could be really small, or they could be really big, or even really huge. And what we want to do is actually put a number on how big they are. We want to put an actual number that describes the amount of region that they cover. If they're small, they will cover a small region. If they're big, they'll cover a big one. So the way we do that is by imagining certain units, or square units. For example, this one, suppose we imagine these units are this big. Then we could have 1, 2, 3, maybe 4 in there, and one. So that one way to describe how big the stuff inside is to describe how many of these squares we can fit in here. And although that one didn't come out too well. Now it did. So one way to describe this one is to say, hey, it's pretty big. You could fit 8 of these little squares that are this big, and that would be an alright way to describe how big the rectangle is. And so we have this notion of area, and which is the number of certain units that fit in there. These units could be square inches, or square meters, or square miles for a city. They describe how big the area is. And really, another way we could define it would be to simply say how many of these units are here. For example, 4, and how many are here. There's 2 that fit here. So we could define area as the number of these units that fit in the base times the number of units that fit in the height. So often we say that the area of a rectangle is b times h, which represents base times height. Because of this, 4 times 2 is 8, meaning that you can fit 8 of these little squares. So if these were inches, you would say, hey, the area for this is 8 square inches. Maybe written like this, 8 inches with a little square. If this was a city and you were talking about miles, maybe you would call them 8 square miles and whatnot. Anyways, that's the area of a rectangle. That's probably what you're used to seeing. You can compare that with maybe a larger triangle. Suppose we had a triangle like this one, and suppose this one grew just a little bit more. You'd obviously think, well, this one's got to have a much bigger area, and we can just sort of guesstimate using the same type of units that we had before. Maybe you can fit 4 there. Maybe you can fit, I don't know, let's say we could fit 1, 2, 3, 4, 5, 6, 7, 8. 8 here, and 4 tall. So you could, if you broke this down to the appropriate little lines here, and you get rectangles out of it, assuming they're all the same size. I know they're not, but you get the idea. You get 32 say square inches. Supposing we were talking about inches. So that's the idea for rectangles. It's quite easy. Quite natural, and then it gets a little bit more interesting when you're talking about objects other than rectangles. For example, let's take a look at this object. As it stands, this is if these are 90 degrees, which for now we can assume they are. This is called a parallelogram. Sorry, it's called a rectangle, and also a parallelogram. But supposing we mess around with it for just a little bit. Suppose we tweak it just a little bit, and suppose we abandon the idea that these are 90 degrees. Suppose the only thing we maintain is that these two sides are parallel. Then maybe the rectangle could look something like this. Whoa! Now it's no longer what we call a rectangle. Now it's what we call the parallelogram. And the question is, well, how would you figure out that area? Because it's not quite as easy to fit nice, perfect squares into a shape like this, right? So this may be a little bit more interesting question. So the interesting question is, if you start off with a rectangle like this, assuming these are 90 degrees, what happens when you shift this guy just a little bit, maintaining the height exactly the same? All you do is slide this over that way or that way, a certain amount, whatever, maybe even this much. The question is, how does that affect the area? Does it decrease it or increase it or maintain it the same? And the answer, amazingly enough, is it'll keep it exactly the same. And one way to see that is to see the following. Imagine that you could maybe cut this guy right here. Maybe you had some magical scissors here, and you could cut it. Cut it. You could take this piece here, and you could add it and put it. This is exactly the missing piece over here. I'll just make my dashed line here. And so this triangle that you could cut off, you could actually fit over here, and this part would be gone. And then the question is, how big is this area? Because that's exactly the same area as before. You just took a certain piece of it, you put it over here, and now we could assume that these you might have to think about it a little bit, but you could make an argument that these angles have to be 90 degrees now, and you've got exactly what we had before, which is the shape of a rectangle, something that we already know how to do. The area of a rectangle is base times height. So therefore the area of this would be this base, whatever that may be, times the height, which is the distance between the parallel lines. And so the area of a parallelogram is exactly base times height, just as it is for rectangles. And so here's an example. Suppose you had a parallelogram that went something like this. Suppose the bottom was 8, and this side, we don't even know how long this side, but suppose the vertical distance here, this side was 4. Then what we just discussed here would imply that, and correctly would imply that the area is equal to the base times the height. 8 times 4, which would be equal to 32. Okay, amazing. The moral of the story is that this idea of moving the top, sliding it over this way, does not affect the area. You could slide it as long as you maintain the height the same and the base the same. The area stays exactly the same. Amazingly enough, you could even move it all the way here. As long as I've maintained the height, that shape right there. Let's copy that. Copy. Let's put it over here. So this shape right here, amazingly enough, has exactly the same area as long as I maintain the height the same, exactly the same as that shape right there. Can you believe it? I know, huh? It's amazing. You could stretch these forever and ever and ever. As long as you don't change these, the area remains the same, and then forever. The special formula for trapezoids will be something like this. It will be, you calculate the base here, you calculate the height here, make sure these are 9 degrees, so then we can call it the height, and you don't worry about how slanted these sides are. We will always conclude that the area is equal to base times height. Okay? I know, huh? What else do we got to do? All right, so that's the rectangles, no problem, base times height. Trapezoids, no problem, base times height. The next thing we want to consider is what happens if you don't have a trapezoid. What happens if you actually somehow manage to change the base on one of the, maybe they're still parallel, but maybe you change the size of one of the bases. And here it might take a little bit more interesting reasoning. So let's think about that. Let's get serious on this one. So the question is, how does this affect the area if I leave these lines parallel, but I change the size of one of the bases? For example, say the top base. It doesn't matter the top or the bottom, to where they're no longer the same size. Maybe this top one's very, very small, the bottom one's much bigger, or maybe I change this one to amazingly large number like that. Now That's no longer what we call a parallelogram, but a trapezoid. So the question is, how do we calculate the area for that? And here's a nice idea. You could just take that guy and make a copy of it, and then what we could do is just twist it around here. Let me think. I think I could twist it this way. No, I think I could twist it more that way. Wait a minute. Maybe I can move it. Just to I want to fit it right here, so let's move it right there. Let's move it right there. Let's put it right here, to where it fits perfect. It needs a little bit more twisting, so we'll twist it just to make it fit perfect. And it's gonna fit perfect because it's well, I'll let you think, but the basic story is that Euclid said a long time ago, these are parallel lines, this is transversal, so alternating interior angles have to be congruent. But without getting too much into that, suppose we could provide a convincing argument that they really are parallel now, and that this side will fit exactly perfect on this side. Now what? How is that going to help us solve the original problem? The original problem was how do I find the area of that guy right there? That's the problem. So what I made is I made another one. So now I got two problems. But they're much easier problems, because now look at that. Now what I have is, of course, a trapezoid. And for trapezoids, we've got that one down. We've dominated that. So for trapezoids, the idea was you would take the entire base, we'll call it big B, times the height, right? So if we could calculate the height here, h, then the area of this whole area is big B times h, just as we had calculated before, base times height. But there's a problem here. The problem is that this area is not the area of the original problem. That area right there would be the area for two of those original problems. So really the total area for the original problem would have to be that divided by 2. Does that make sense? Because I have two of them, two of these pieces. And more than that, now I got to figure out how do I calculate the big B here. The big B is the total of the bases. The big base of the original problem plus the little base. So if I call this, I'll call this B1 for one of the bases, and I'll call this one B2 for the other base. Then the big B, the big base here, would be equal to. You guys should say something. Can't see. All right. So then the big base would be B1 plus B2, of course. So then I go back here and I can conclude something very, very important and very, very famous, namely that what can I conclude? If I take something like this, that I can conclude that the area is equal to, and I've called this B1 and I call this B2, two bases, then the area is equal to B1 plus B2 times the height divided by 2, where this is a height. This is h, the one that makes a perpendicular line with both those. And there's the super famous formula for a trapezoid. And I'll try to interpret it a different way. Another way to interpret it is that you take the average of the bases. If you just cover the h here, the b1 plus the b2, that would be the sum of these divided by 2. That gives you the average of the bases. So you could think about it this way: the area is the average of the bases times the height. When we had trapezoids, you didn't need to do that because both bases were the same. This base was 8, that base was 8, so there was no need to take the average. The average would be, of course, 8. The trapezoid discussion says, hey, don't worry about it. If they're different size, just take the average and play the same game, a similar game to what we did with parallelograms. Okay, so maybe a couple examples are in order. Take this example. Suppose that This area is 4, and this area is I don't know. Let's just say 8. Suppose that this height right here is 5. Well, it's a piece of cake. What we do is we add these 8 plus 4 times the height. That's one way to do it. That gives you 2 of these, but then you have to divide it by 2 to just get one of them. That would be a perfect way to do it. So that would be 12 divided by 2 is 6. Gives you a total of 30. Or another way, like I said, another way to do it is say, hey, take the average of the bases. This base is 8. That base is 4. The average would be, their sum is 6 divided by, their sum is 12 divided by 2 is 6. The average, if you average them out, you'd get 6. So it's just 6 times 5, which is equal to 30. That's another way to think about it. Okay, 2 powerful ways to think about it. Super famous formula for the area of a trapezoid. Okay, that was easy, right? Alright, so where else do we go from here? Maybe another example. Suppose you've got another trapezoid here. Suppose that this one has base 100 and this one has base 50 and this one has height 10. How'd you do it? Again, you could just plug it into the formula. You add these bases, because you imagine taking another one and flipping it over here. You'd get 100 plus 50 times the height divided by 2. That would be one way to do it. Or the other way would be just take the average of the bases. If this is 50, this is 100. The average would be 75. 75 times 10, which would be 750. 750 square inches, square miles, whatever you've got going on here. That means if these were 100 inches, 100 inches long, 50 inches long, 10 inches long, that means in the entire area you could fit 750 little square inches. Little bit tiny square inches. Alright, whatever. Alright, so then the next thing we got to do is talk about, maybe finish the discussion. This is an easy discussion, by the way, easy lecture. If we can get this little machine to work. There we go. Something timeless. Right triangles. So this is the first one that's not a quadrilateral. And the question is, how do we get them? Well, similarly to the other ones, what we want to do is maybe use a little creativity here. You could take a copy of this and just maybe flip it to where it fits exactly. Let's see if we can fit it right there. Well, almost. Maybe just turn it just a little bit to fit perfect. Oh man, close enough. There you go. So if you do that, then that means you have two of these. That means that just from looking at it, 2 of these guys make a rectangle, a perfect rectangle. So then the area is really easy because we had already conquered rectangles a long time ago. The area of rectangle is the base times the height. So for our rectangle, we could call this whole base, we could call it B, and the other one we could call A. So therefore the area for this rectangle would be base times, whoa, let's do some classic stuff. Let's call this one H, 4 height. So the area would be base times height. For the rectangle, but of course a rectangle is made up of 2 of the original triangle questions. So if two of these make base times height, then one of them would have to be base times height divided by 2, of course. And so there's your area, base times height divided by 2. Super famous. You probably heard about it. The area of a rectangle is the base times the height divided by 2. It's clear because you could take another copy, make another, put it over here, and you get a rectangle out of it. So maybe a couple, maybe one example or two are appropriate here. So suppose that you've got a triangle here where this is 2 and this is 4. Okay. Then if this is a right triangle, what we just discussed here would imply that the area would be the base times the height divided by 2, which of course equals to whatever. So that means that 4 of these squares could fit in here. If this were squares, well, you have pieces here left, not exactly nice, but with 4 of these pieces, exactly 4 of them, you could fill in all the holes. Okay, here's 2 of them, maybe here's 3, maybe here's 4. Oh yeah, that's exactly right. 2, well, this is nice. 1, 2 squares, 3 squares, and 4 squares. Exactly 4 squares. I told you the area is 4. That's why they pay me. Okay, that was fun. Okay, let's see. So rectangles are pretty easy. Base times height. Check. Parallelograms are pretty easy. Base times height. Check. It doesn't matter how much you pull this side off to the sides. As long as this base and that base are the same, you just do base and they're parallel. You just do base times height. Check. Trapezoids, there's no problem. If the bases are different, you just take the average of the 2 bases times the height. Check. Right triangles, it's no problem. You make another copy of it, so that gives you base times height. For a rectangle, take half of that. That would make your triangle. Base times height divided by 2. Check. Only one thing left to discuss for today, unfortunately. Okay, so the last thing to discuss is what if the unthinkable happened? What if this triangle right here was not a right triangle? Whoa! What if it went all sorts of crazy things like this? Whoa! What would happen then? So then, if that happened, then you'd have to abandon the idea that it's a right triangle. That idea is gone. So this part of it has to be. You have to forget about that. It's no longer a right triangle, but just a triangle here. And same thing here. You can't assume that it's a right triangle. And the question is, whoa, how would you find the area for that guy if it's not a right triangle? And we'll play the same trick that we've done before. What you do is you take a copy of this and you make another copy and you twist it all around, and not so much, and then you move it and you fit it right next to it. Of course, it's no longer, and you guys can guess what kind of shape it's making, right? Of course, it's no longer right, so forget about that right stuff. But what kind of shape does it make? Of course, it makes none other than a parallelogram. Check it out. If you need some convincing, think about it. That makes a parallelogram when you fit 2 triangles. Even if they're not right triangles, I don't care. Any 2 triangles that you take, they'll make a parallelogram. And then it makes it easy to find the area of the parallelogram. Of course, for our original triangle, all we'll do is divide it by 2 because it took 2 of them to make one parallelogram. Was that too fast? Easy, just rewind. I'll say it again. 2 of these triangles make one parallelogram. So whenever we calculate our area, as we already know how to do over here, So when we calculate our area, we just remember that it took two of these triangles to make it, so we'll divide by 2. Alright, talk is cheap. Let's do it. So, how do you calculate the area of a parallelogram? You would need to calculate the base here. Let's call it something like crazy, like B for base. And then we calculate the height here for the triangle. Well, it would be height for the parallelogram. Let's call that H for height. Can you dig it? So then the area of the parallelogram would be, let's recall, what is the area for a parallelogram? It is base times the height. As simple as that. Just remember, if you forget, you could just sort of push this thing back so it makes a perfect right triangle, or makes a perfect rectangle. Then it's very, very clear that it's base times height. Okay, that was just a little rewind. So for this one, let's see, for this one, zoom in. The area for parallelogram would be the base times the height. And then I remember, hey, that's fine for the parallelogram, but that means each of these has to be base times height divided by 2. Base times height divided by 2. That's it. So we did it. In other words, for a triangle, even if it's not a right triangle, let's see if we can do that. Even if it's not a right triangle, in other words, suppose you'd have to abandon this right triangle stuff, still the same thing is true. All we do is find out the base and the height. So whatever the base may be, let's call it B. And you find out the height, which means you have to take the highest point of the triangle and drop a perpendicular, and that right there, that would be your height. Then it's settled. The area for this is base times height divided by 2. Notice it is exactly the same as the area for a right triangle. So really there was no difference. At the end of the day, the area for all triangles, not just the right ones, the area for all triangles is base times height divided by 2. Let's check out a couple examples here. Suppose you've got a triangle here where the base is 10 and the height is 2, and you want to know how many square units would fit in here. Our discussion would tell you, hey, I know exactly how many. It would be 10 times 2 divided by 2, which would be equal to exactly 10 square units. Just like that. See how easy that is? Again, if you had a triangle, the base was 6 and the height was 16 and the height was 5. The area would be base times height divided by 2. Just like that. Easy, huh? I make this stuff look easy. That's why they pay me insane amounts of money. Alright, we'll see you guys. Peace.